Hi friends, this is Anusha. Welcome to Anu Online Tutorials. If you like our video, please share to your friends. Don't forget to subscribe and click on bell icon. So today, let's start our lesson. Our session is about today refraction of light at curved surfaces. So what is refraction of light? As we have studied in the lesson 1, the reflection of light. You know about all the things about light, isn't it? And what is reflection is something different from refraction. Reflection is something different of refraction. So we are going to discuss more about this. The palmist, even they use some scientists and doctors will also use some lenses. Why they use lens? With the lens, they can clearly see the object. Whatever they want to see, they can clearly, easily, even with cameras. Okay, and all also will use lenses. Lenses are very, very important in our life. Lenses are very, very important in our life. Before we learn about mirrors in the first lesson, the behavior of a light, the both lenses and the mirror depends upon the light behavior. So the light mirrors you have learned already, isn't it? And lenses you have learned about this mirror. In both the light plays important role. Which plays important role? Light. The both says about light phenomena. We learn about the light behavior of the light itself. But the mirrors. In the case of mirrors, to know how light behaves in the mirrors, mirrors, the light in the mirrors will be given by reflection. Will be given by reflection of the light. Reflection of the light, how light behaves in the case of mirror, the reflection will be given, and it is nothing but reflection. Reflection will give you, otherwise, in other words, you can say light behavior, how the light during the reflection. The light, reflection, mirror. Reflection is mirror. You get that point. Refraction is something different. Don't get confused with the two words. The light, reflection, mirror. In the mirror, how it behaves. You know, concave mirror, convex mirror, and so many principal axes and all you have learned in your first lesson. And how light behaves in the lens. Light behaves in the lens is the refraction will give you it. What is refraction actually? What is this new word called refraction? You know what do you mean by reflection? Reflection is something that when a light hits a body which through which the light can't pass through, opaque object, then it bounces back. About the reflection, you know. Refraction is something different from reflection. Refraction is something different from reflection. Refraction is that when a light in the reflection will carry on in the one media, let it be air or any one media it carries out. But in refraction, when light is passing from one media to another media, from one media to another one, let us suppose say from gases to solids or solids to gases or liquids, how the light behaves. So let me, how the light behaves. In the class 9, you have learned about these refractions, how the refractions takes place. Only with a few things I want to give you an introduction to you. So let me tell. What is, first of all, we will see what is refraction. What is refraction? What is refraction? Refraction is something in which when when a light passes from one media to another media, one media to another media. You know, light travels in a straight line. You know it, isn't it? Suppose this is water. And this is air. This is water. This is what? Water. And what is this? This is air. Water and air. When light is traveling from one media to another media. Air is one media, water is another media. Air is one media, water is another media. When it is traveling from one media to another media, instead of, see, naturally the wave, some object source, it will be traveling like this, isn't it? But when it is traveling from one media to another media, it slightly bends. It slightly changes its direction, you can say. Changes its direction. The changes its direction is nothing but, this is the normal. When, see, changes its direction. When it changes its direction, it changes. This is the instant ray. This is the refracted ray. What is this? This is what? Refracted ray. This is instant ray. And this is refracted ray. Refracted ray. So when light is traveling from one media to another media, when light is traveling from one media to another media, at interface, what do you mean by interface? What do you mean by a new word called interface? What is this interface? Interface is nothing but where these two medias meet. A line will be there where the two media, the light has to change from one media to another media, isn't it? From one media to, suppose this is the air above, this is the water down. There will be a one border, you can say, one border where the light enters from air to water. The surface where the light enters from one media to another media is nothing but interface. It is nothing but interface. So in one interface, what happens? Light travels from this is called radar media, and this is called, water is called denser media, isn't it? So when light is traveling from one media to another media, it seems that it is going to get, it is going to bend like this. Why this bending? Why it appears to be? Actually, if you see from outside, it appears that it is something bending out. Why it appears like that? Why it appears? Because light changes. You know, the light is different. Speed of the light is different in different media. Speed of the light is different in different media. So the light just does not change any direction. It does not mean that exactly it turns like, no. It changes its speed. So it travels speed in rarer media compared to the denser media. It does not, only air will be the rarer and water it does not fix like that. It depends upon the density of the media, diffractive indexes, different media has different refractive indexes, isn't it? So depending upon different indexes, refractive indexes, they will be changing. I hope you are understood. It's nothing but reflection is something that when something hits, light hits something, it bounces back. It's a reflection. Refraction is something that when light is traveling from one media to another media, it changes its direction, speed in travel. So the light appears to be bent. The light appears bent towards the normal. This is a normal. You know what is normal? In the reflection lesson you have learned. Perpendicular to this, isn't it? So refraction. Next, you can see this. See, it seems that the pen is bent here. See, this seems that at the point of interface, the pen seems to be bent like this. Can you see clearly? It shows that pen is bending here. Pen does not bend. Pen will be like this only. But when a light is traveling from rarer media air to denser media water, air to denser medium water, at the interface it changes its speed. When it is entering into another media, it changes its speed. You can clearly see this. See, when it is entering into another media, it clearly seen that it is, see, it is bent, isn't it? It is nothing but refraction. At the interface, when a ray is moving from one media to another media, it bends. It is nothing but your refraction. Nothing but your refraction. So, the refraction we will learn in the case of lenses. How the lens is very, very important, already I told you. In the cases how the lens behaves, how the lens works. In the case of all these things, we will use what? Lens. We will use this lens. Lens is very, very important topic. So, when light behaves in different way, in different media, I said you already, the speed of the light will be changing. And in this, like our mirrors, there are two, mainly two. These are also from spherical mirrors only. We will think that they have cut from the spherical mirrors only. Two important things are there. Those are convex lens and concave lens. Convex lens and concave lens. So, what is this convex lens and what is this concave lens? Convex lens will be something like this to you. Concave lens. Convex lens will be broader at the middle and thin. Thick at the middle and thin at the edges. And this thin at the middle and thick at the edges. Concave lens. Concave lens. Convex lens. Concave lens. It will be bulged like this. It appears to be bulged like this at the middle, and it will be thin at the edges like this. And it will be thin at the edges, and when you come down, it will be bulged. It will be bulged. And next, we will clearly learn about this convex lens and concave lens, and how these concave and convex lens behave, and what are the important terms need to be noted, and what are the easiest way you need to draw the ray diagrams. Everything clearly without any doubt. I'm surely going to clear. Just you see, this is the convex, concave, refraction of light at curved surfaces. You know, curved surfaces are this. When curved surfaces, not a plane surface, curved surfaces. So, in detail, without any doubt, I'm going to explain you now. Now, I want to show you one more experiment also. Did you get clarity with this? And another one I'll show you. So, take a paper. In that, you draw a arrow line like this. Arrow, ray like this. Okay, ray you have drawn. And see from the curved surface. it appears to be diminished. It appears to be diminished. Why? As the ray is traveling from air to a curved surface is there and into the air, and again it reflected. It is reflected 2 times, isn't it? It is reflected at this surface, and again the what you are seeing from there, this surface, it get refracted, isn't it? So it seems to be diminished. If I pour water in this, means what? There are 3 mediums now. There are 3 mediums. Air. There are from the air, it has to enter into the water, and it has to again come out. It has to cross 2 mediums, isn't it? See here. See, when it is like this, it seems that it is inverted. The arrow will be seen this side. You see, the arrow is seen this side. Can you see? At this side, arrow is seen this side. See, arrow is seen this side. Arrow is seen this side. Inverted. Actually, arrow is towards the arrowhead. The mark is towards the left. But when I pour water in this, it seems to be inverted like this. This side arrow mark is seen this side. Why? Because the light has to get refracted. This acts as a curved surface. This is interface, I said, isn't it? It changes its speed, I said. And one more I need to see. It changes its speed. The light changes its speed when it is entering. Where it changes? At interface it changes. At interface it changes the speed. Now, what is a lens? Lens, a piece of transparent bounded by 2 spherical surfaces. See, in the mirror only one side will be there, mirror, and other side will be, I said you already, right? For a concave or a convex, one side it will be like this, and the other side will be closed with the aluminium or something, I said, isn't it? The silver or aluminium, so that the light does not go that side. But in the case of lens, it is not like that. Lens, a piece of transparent bounded by 2 sides. 2 sides you can see, like glass like thing will be there. 2 sides glass will be there. 2 sides like your spectacles. 2 sides glass will be there. 2 sides glass will be there. And convex. In this lenses again 2 types. Convex, concave. Convex is something which is thick at the middle, center, and thin at the edges. Thick at the middle and thin at the edges. And concave is thin at the middle like this and thick at the edges. So let me tell you how light behaves when it passes through a curved surface. When it passes through a curved surface, let me introduce, and later I'll come how it behaves in the lens. Okay, first let me explain how it behaves in a curved surfaces and what are the terms here you need to learn. Let's go with that. So, in previous experiment I have shown you, isn't it? So, the air is one media and water is another media. Suppose this is the air is one media and it is separated by a curved surface. With the help of this glass I have shown you that is separated by a curved surfaces. Suppose how the light behaves in a curved surfaces, let us know. So, this is the curved surface. What is this? This is the curved surface, and these are the lights rays falling on this curved surface. Light rays falling on the curved surface. So what happens? This is C, center of curvature. What is the center of curvature? From the spherical mirror I have taken this curved surface, isn't it? From the spherical mirror I have taken this curved surfaces. So the center of the spherical mirror is nothing but your center of curvature. Otherwise you can say where all the normals meet. From the center of curvature, if you draw a line like this, a line like this to the curved surface, it is called as a normal. Normal will be changing from point to point. See, this is a normal at this point. 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 So a line joining, when you join a line from center of curvature to the curved surface, that line is called as a normal. And this is the center of the sphere, I said, isn't it? Spherical mirror. And this is the center of the curvature. I mean to say the curved surface. The center of the curved surface is nothing but your pole, you will call. Okay, and this is the principal axis. The principal axis joins both the pole and the center of curvature. I hope you understood. A line drawn, see, a line drawn from center of curvature to the curved surface is nothing but your normal. And see here, when a ray is traveling from, when according to Snell's law, you know, when a light ray falls on the normal, then it does not get deviated. It does not get deviated. So, see here. Suppose, see, this is air. This is water. Suppose, think that this is water. This is air and this is water. Two different media, isn't it? Denser and rarer, you can say. Rarer media, denser media. So, when a ray, any light ray falls on the principal axis, it is a normal. Principal axis, normal to the surface, isn't it? Principal axis, normal to the surface. Then it does not get deviated. It does not get deviated. It refracts back in the. It does not get deviated from the path. And when it is normal also, when it is drawn normal also, it does not get deviated from the path. It does. I hope you understood. In the two cases, the light does not change its path. Only two. In the case of refraction also, one is principal axis and one when it is passed through the center of curvature. Normal, you can say normal. When it is making a normal to the curvature, then also it does not. At the two normals, the light does not change its path. And next, case 1. See, suppose this is the rarer media, this is denser media. Rarer media air, denser media water, suppose. Rarer media is air and denser media is water, suppose. See, when a ray is traveling, this is what convex surface I take. I don't say it is a convex mirror. I am saying that is a convex surface. Convex mirror is something different from convex surface. Don't get confused with the convex mirror and convex surface. I am not saying it's a convex mirror, it's a convex surface. So, to explain you, from the basics I want to bring you to the lens. So, I am explaining you. See, when a ray is traveling parallel to the principal axis. See, this is a normal. From the center to the surface of the curvature I have drawn, that is a normal. So, from the parallel to the principal axis, from rarer to denser it goes. It moves towards the normal. When it is parallel to the principal axis and this is a normal. See, it moves towards the normal. This is also a convex surface. See, when a ray is traveling parallel to the principal axis. And this is the normal, isn't it? It moves away from the normal. This is what denser media and this is what rarer media. When the speed in the denser media is less compared to the rarer media. So if in denser media the light goes somewhat slowly compared to the rarer media. When it goes rarer media, it moves immediately. See, the speed increases more. And this is the third surface, that is concave surface. This is what concave surface. This is what concave. This is convex, this is convex, this is concave surface. This is what concave surface. So when a light ray This is a concave surface, isn't it? Inside like this, the surface will be. When a light ray is traveling parallel to the principal axis, when a light ray is traveling parallel to the principal axis, when a light ray is traveling parallel to the principal axis, this is a normal. This is a normal. The line drawn from center of curvature to the to the surface is normal. See, when a light is traveling from rarer to denser, from in a concave surface. See what happens from denser media to rarer media. It is going from denser media to rarer media. This is the denser. Here the surface is denser media. It moves away from the normal. This is the normal, isn't it? It moves away from the normal. It moves away from the normal. I hope you understood. I'm going to show you one more case also. So this is the fourth case. In the fourth case, when rarer to denser, the concave mirror, when a ray is traveling parallel to the principal axis, and it behaves like this, isn't it? It behaves like this. This is the this is the normal. Let it be. Rarer to denser. It moves towards the normal, you can say. It moves towards the normal. So these are the four cases you are going to learn. And here is one formula for the curved surfaces. Here is a formula for curved surfaces. So this is a curved surface formula. N2 by V by N1 by U is equal to N2 minus N1 by R. Where V, U, R, radius, you know it. V, you know image distance, object distance, R. And now, if this is used, derivation and all is given, but derivations normally does not come into exam. It's not so important in the exam. So only the formula is important. We need to do problems on this formula. We are going to learn. If it is a plane surface, curved surface, okay. If it is a plane surface, R you need to give it to the infinity. R tends to the infinity. The same formula, R tends to the infinity. So the formula becomes like this, isn't it? N2 by V minus N1 by U is equal to 0. So N2 by V is equal to N1 by U. This is your plane mirror formula. If it is a plane mirror, with curved mirrors, this is N2 by V minus N1 by U is equal to N2 refractive index of second media, refractive index of first media, refractive index of second media to the refractive index of first media. In the case of plane mirror, R tends to infinity. In the above formula, R tends to infinity for the plane mirror. Okay, if two refractive indexes are given and image distance and object distance is given, they ask you to find R, or they have given R and they ask you to find V. Any of them you can do this. And in this, the plane mirror returns to the R tends to the infinity. R tends to the infinity. And with this, you are going to close curved surfaces, and we are going to enter into lenses. Lenses introduction I have given you, isn't it? Yeah, we have learned about lenses, and different types of lenses are there, concave, convex. As you have learned in the mirrors, it will be very easy to you. If you are perfect with the mirrors, it will be very easy to you. But there is a slight change in this. As you have learned in your mirrors, here also optic center. Optic center is nothing but hole, you will call that, isn't it? And principal axis, focus, focal length, everything is same. All the terms will be almost same, but small changes are there in this. So what is this? When you see this, what lens? As I said, always in the mirrors, In the mirrors, one side should be mirror and other side should be closed. But in the case of, it is a transparent sphere, isn't it? It is a transparent glass, you can say, which when both the sides are bonded like this. Both the sides are bonded like this. This is a the mainly we will use, there are different types of lenses, double concave lenses and the concave lenses, concave or convex lenses, different types of lenses are there. But mainly we will use concave lens, convex lens, and concave lens. To some extent we will learn only a few things about the convex lens. Concave lens, very few things. In the case of this is convex lens. How the convex lens will be? It will be bulged at the middle and it will be thin at the edges. Isn't it? It does not come curved like this. But when you see a lens, you don't find this bulginess, there's all these things. When you keenly observe it, then you can find out. Otherwise, you can't. And so there are two bounded surfaces like this. And see here. See, the important terms to be learned is, first one is optic center. What is this optic center? Optic center is nothing but it is the center of the lens, you can say. It is the center of the lens. Actually, with the C it is represented. C does not mean that it is the center of curvature. It means optic center. C it will be measured, or O, it's okay. O we will take, because C, if you see, you may think that it may be center of curvature. It is a center of the lens. Here also the same, center of the lens. See, and this is a line joining. The line joining center of the optic center is called as a principal axis. This is what? Principal axis, you have learned there. And what is the focus here? What is the focus? See, when the rays are traveling parallel to the principal axis, then all after refraction, there will be a slight bending here. When you are drawing the refraction, you need to take care that when it is changing the media, you need to lightly bend it. Because it is a case of refraction, isn't it? You need to show a slight bending of the light. So, from when it is traveling parallel to the principal axis, all the rays will meet at one point. All the rays will meet at one point in the case of convex lens. In this, convex lens is a converging lens. Convex lens is the important point to be noted is convex lens is the converging lens. Convex lens is the converging lens. Don't forget, convex converging, really they meet. Light rays converging here, converges, they meet, they come and meet here. The light ray really meet here. The light rays converge in the case of convex lens. So all the rays will be meeting here, and this point where all the rays meet is called focus. You know already. That is called as focus or principal focus, or simply you can call it as focus. Principal focus or focus, both are same. And see, if suppose I have drawn this side, isn't it? If the rays are coming from that side parallel to principal axis, they all will meet here. As I have two transparent surfaces, two focuses will be there. And when the ray, not to have confusion, it is capital F, you know, focal length is small f, isn't it? Focal length is small f. And the focus is f. So, f dash. When the light rays are parallel to from other side of the transparent sphere, when lens it will come, then they are going to meet here. Both are going to be at same distance from the optic center. Both the focuses will be at the same distance from the optic center. This is called optic center. Instead of pole, the lens, you will call it as optic center. Here, when the rays comes from here, they are going to meet here. When the rays are going to parallel to principal axis, they are going to meet here. And you know, when it is, as I said already, when they pass through the principal axis, it does not get any deviation in the case of principal axis. Now it is clear, I hope. And the distance from the optic center to the focus, is nothing but your focal length. Nothing but here, focal length. Nothing but here, focal length. They are converging really. So the rays are converging really in the case of convex lens. I hope you are clear with optic center, principal axis, focus and focal length. And this is also same. But here, this is a concave lens is a diverging lens here. Concave lens is a diverging lens. Concave lens is a diverging lens here. Concave lens is a diverging lens. And see here, after refraction, see, slightly bend I said, now they are going to diverge. They are going to diverge from the surface. After refraction, what happens? They are going to diverge from the, as I said, they are going to diverge. It is a concave, they are going to diverge. And all has to meet here. See, they are meeting here. I am making it to drag the rays back of the lens, and I am making surface, and I am making here to meet. So it appears to meet here. So this is called as a focus, and that side of the focus is f dash. Okay, if the rays come from this side, when rays come from this side, they are going to diverge this side, isn't it? And if I drag them back like this, they are going to converge. They are going to meet. It seems to meet at this point. Both will be the same, and the distance between the optic center to the focus is nothing but focal length. Principal focus, all are the same. Let me give you very important. These are very important. Don't get confused. Two will be there. In the case of mirrors, only one, isn't it? That side will be closed. So there is no problem. Here, two sides will be there, isn't it? So you are not supposed to take focuses on the two sides. Got it? I hope you got it. Let us see the rules. You have saw in the mirrors, isn't it? The rules to draw the object, when an object is placed at different places where the images are formed, different rules are there. Let us see in this also now. Here are some rules to follow while you are drawing image, to find the position of the image and how the nature of the image and all. You know very well that where two rays meet, there the image is formed. From the object, let number of rays come out, but where two rays meet, minimum two rays has to meet to form an image. So to form an image, two rays need to be meted. It is compulsory. So some rules you need to follow while drawing those images. How the image behaves in convex lens, we will see. Lens, convex lens, always diverging lens. Convex, diverging, convex lens, diverging lens, convex lens, diverging lens. So see here. The first rule comes here is a ray parallel to the principal axis of a convex lens passes through its focus after refraction through the lenses. Passes through see here. Here is a ray from the object, some object it is coming. This is the ray. A, D, E, X is a ray, isn't it? So A is a ray. It is passing at D. At this surface, it is C. I can write C, I said, isn't it? This is the optic center, I said, you already see. Nothing but optic center. Yeah. Oh, C, optic center. Yeah. See here. When a ray is traveling, it is suffering a refraction here. It is suffering a refraction here. After the refraction, when a ray is traveling parallel to the principal axis, this is the principal axis, X dash, Y dash is the principal axis, L is a convex lens, and A is traveling like this. It is getting refracted here. After refraction, it passes through. After the refraction, see the arrows, it is very clear. After the refraction, it passes through the focus. It passes through the focus. At the D, it's a first refraction. That's why I have made it. Minute points you need to note it is here. I made the ray to bend here. See here. I made the ray to bend here, and it passes through the focus. A ray of light passing through the optic center of a convex lens goes straight after refraction through the lens. See here. See, when it is traveling through the optic center, when it is traveling, a ray is traveling through the optic center. Let us say x dash, y dash here is principal axis, f dash, x dash, y dash is the principal axis, f dash, f are focuses, and c is the optic center, l is the lens, and a y is the ray. AY does not suffer any deviation. Did you notice the point? It does not suffer any deviation. It does not, see, a ray of light passing through the optic center, a ray of light passing through the optic center of a convex lens goes straight after the refraction through the lens. After refraction through the lens, it goes straight. Okay, next point is, third rule is, a ray of light passing through the focus, a ray of light, see, x dash, y dash is the principal axis, x dash, y dash is the principal axis, c is the optic center, and when a ray is traveling ray is traveling through the focus here, when a ray is traveling through a focus here is a focus, focus, when a ray is traveling through the focus, and after the refraction at D, it suffers the refraction. At D, it suffers the refraction. After the refraction, it travels parallel to the principal axis. If it is from that side, suppose that side, it comes here, it travels parallel like this. Got a point? This side or the other side? Both the sides you can take it. And these are the rules you are supposed to use while you are drawing the images. How the images are formed at different distance. The object is kept in different places. So let's go with that session. Let us go with that session now. So this is the case. Object at optic center and focus. An object is kept at between the optic center and the focus. And here is a convex lens. Here is also a convex lens. But here, instead of drawing this lens, you can draw convex lens like this also. Like this one line. Convex lens. Convex lens you can draw like this simply. Instead of drawing this big one. And concave. Caves, I told you in the mirror also, isn't it? Caves will be up like this. Concave lens. Simply with the symbols, they'll draw it. There is no difference in the formation of image or formation of anything like that. They just for your convenience they have given. Convex lens is like this, concave lens is like this. So see, before I am going to this, I want to explain you. See, each lens is a part of the sphere. Each lens is a part of the sphere, isn't it? So the sphere will be having a center of curvature. This curved surface will be having one center of curvature, and this curved surface will be having another center of curvature. The distance from the center of curvature to the surface is nothing but your radius of curvature. A simple I want to give you, because I have kept here C1 and C2 so that you need not to get confusion. These are the center of curvatures of these two lenses. So where is the two lenses, teacher? Here two lenses are there, here no two lenses are there. Two lenses I have said, they have their gap between this, to our understanding I have drawn this one broad one, but the gap between them are very minute. You can't even tell that they are two transparent surfaces are joined. They are very negligible, you can say. Okay, for your convenience I have drawn like this. So that is a symbol of what? This line and the arrow mark is a symbol of what? Convex lens. What is that? Convex lens. And see here. See here now. This is the lens. Which lens is this? This is your convex lens. What is this lens? Convex lens. What lens is this? This is the convex lens. So what happens? The first case is when object is kept between the center of curvature to the focus. Between the center of curvature and the focus. Center of curvature and the focus. Center of curvature and the focus. This side. And when it is kept like this, AB is the object. AB is the object. And one ray, according to the rules of rays rules, one ray traveling parallel to the principal axis passes at the D. It suffers refraction. The this parallel to the principal axis suffers refraction at D, and after the refraction it passes through the focus. After the refraction it passes through the focus. And next case is when it is from the center of curvature it passes, it does not bend, it goes straight, it does not bend. I will not show you here the refraction. It does not bend, it goes straight like this. It should not bend like this at all. It should not bend like this. The straight way it has to go. It should not bend here. It should not bend. Okay. This is the incident ray. And this is the refractor ray. With the red color I have mentioned refractor ray. It does not bend, it goes straight. So when you see from here, it seems that the object is formed here, and behind the lens it is formed, and it is enlarged virtual, as the rays does not meet, isn't it? See, here the rays are meeting. Here the rays are really meeting. Where the rays meet, there the image forms. Where the rays meet, there the image forms. But here the rays are not at all meeting. So you need to extend this. Extend this refractor ray from here to back like this. You need to extend it. When you extend, these two will meet here behind the lens, and virtual and erect object, a virtual image, as the rays does not meet really, it is a virtual image, and if it forms erect means straight and larger than the object. If point to be noted is it is larger than the object. The same thing, see here, once again I am going to explain. A object is kept between the optic center and the focus, and here AB is the object, and the ray A is suffers a refraction at D and passes through the focus, that is a parallel to the principal axis, and another one passes through the optic center. It does not suffers any deviation. And these two, from the refracted rays you are supposed to write, not from the incident rays. From the refracted rays you are supposed to extend this. And here the point to be noted is from here, not from here you are supposed to draw. All will draw from here. No, from here you have to draw. And you need to extend this here till here. B dash, A dash. B dash, E dash. A dash, B dash is the object, and erect object is formed, and it is larger than this, and image is virtual, erect and magnified. The same case is this. This and this, the same case. But the shape of this, I have drawn it like this. This is what? Convex lens. Between optic center and F it is kept, and here the image is formed and it is magnified, larger than the object kept at focus. When object is kept at focus, let's say AB is the object, F dash is the focus, F is here focus. A ray is traveling parallel to the principal axis, it passes through the focus. And another one from the optic center, if it moves, O or C, both are optic centers, I said you already, isn't it? Optic centers, if it moves, so it does not get any deviation, it goes in a straight path. And this is the focal length at infinity. Then where these two are going to meet at infinity, these two rays where they are going to meet at infinity, they are going to meet. So we are not drawing any image. Real and inverted image will be formed, and as they are at infinity, they are going to meet the real and inverted highly diminished, very small image is formed. Here also the same with the convex lens. Parallel to the principal axis, passes to the focus, and from the optic center it moves, and the object is formed. See, C1 and C2 is a double. You can sometimes write 2F and 2F dash also. It is I'll tell you in the next case. So this is the case where we this is the case when the object is kept at infinity. I hope you understood. AB is the object, image we did not draw. At infinity it is going to be real and inverted, highly diminished. X, it is going to get deviated at D here. It is D. Refracted not deviated, refracted at D, and moves from the, as it is parallel to the principal axis, moves from the focus like this it moves. Got it? And next case. I hope you all understood this. And next case we'll go with. So next case, third case is object kept between f dash and 2f dash. What is this 2f dash new term? It is nothing but double the focus. Double the focal length. See, this is the focal length f from here to here focus, and double to this focal length is 2f. In some books they have given C1 and C2, and in some books 2f and 2f dash and 2f1. The 2f they have given. Both are same. No need to, the same cases will happen. See here, this is a convex lens, this is a convex lens. A deviation, here the refraction takes place, this is the D. So A is travelling parallel to the principal axis and refraction will take place at D and it passes through the focus. And another one, when from this object, incident rays, these are the incident rays, the rays which are coming from the object are incident rays, isn't it? Incident rays. They are passing through the focus. They does not undergo any deviation. In a straight way, they fall here. Both where the two rays meet, there the object form. Where two rays meet, there the object forms. Remember, this is the incident ray. This is the refractor ray. Incident ray, refractor ray, incident ray, refractor ray, incident ray, refractor ray. As in the case of optic center, when it passes, it does not deviate anything. So it goes like this, and two meet here. Where the two meet, there the image is formed. Where two rays meet, there the image is formed. You should make the rays to meet to draw the image. Remember image. So what here? How the image will be formed? Real image, as these rays are meeting really. I am not extending backside or drawing any dotted lines. They are really inverted and magnified. The same thing here also. Here in between C, they say the center of curvature. The same behavior here. See, 2f or f or center of curvature or C. You instead of C1 and C2, you can raise 2f and 2f dash also, no problem. And here the lens you see, I have drawn here the symbol of the lens, isn't it? So between f and C2, if it is placed here beyond C1, the image is formed. Here the same 2f dash beyond it is formed. Here also beyond it is formed. Beyond 2f dash it is formed. 2f it is formed. It is C1 it is formed. Got it? Your fourth case. When the convex lens is kept here and the object is kept at 2f dash. In that case, the convex lens kept C2. I said you already. In some books they will be written as 2f dash and 2f, and some books they have written as C2 and C1. Both are same. I said you already. So when object, this is the object, this is the object where it is kept, where on the lens the incident rays will form, that is the object. So incident ray will be forming like this, and this is the refractor ray, incident ray, refractor ray, parallel to the principal axis, passes from the focus, parallel to and going from the optic center. They two, where the two, this is a refractor ray, I mean in the green color I have mentioned, isn't it? When the two rays meet, where the two rays meet, there the image is formed. You need to, instead of that, let me give you a small tip. If you can't remember, if you can't draw and these two lines are not meeting it here in the exam, it takes more time. First you draw the image, and after that you draw these cases, so that it will be very easy to you. So see here, it passes, and where the image is formed here, 2f and 2f dash, both are same here. Say at the center of curvature it is kept, at on the other side of the center of curvature. I said two lenses are two bounded, isn't it? Two sides it will be there. So two focuses, two center of curvatures, two will be there always. Two. Here what is there? There also the same thing will be there. The light can fall from that side or this side. That's why the two will be there. So what? These two are going to meet here at the center of curvature. 2f it is meet, and it is real, inverted. What is 2f here? Double the focal length, same as the object, the same size object. If you want, you are supposed to keep at C1 and 2f. Here the same size. This is nothing but center of curvature. In some books they have given as center of curvature. No problem. 2f or center of curvature, anything you get the same. Okay. So it is passing through the object, and here a dash B dash is the image, here is the object. Object, image. Object, image. Here in both the cases, AB, object. A dash, B dash, image. Object and image. So we will go with the fifth case comes is object beyond 2F or beyond C. C1 here. C1, C dash. C1, C2 also you can write, no problem. Let C1, C2 so that you will not have any confusion. C1 and C2. Okay. Now, how the image will be? Beyond A, B it is formed. We are so a line parallel to principal axis get refracted at the surface and it moves from the focus and it is here, and after that a line two rays you need to take to form an image, isn't it? To form image, how many rays you have to take? 2 rays you have to take. 2 rays you have to take. When the 2 rays meet at a point, you say that yes, the image is formed there. So one ray is traveling parallel to the principal axis and meet at passes through the focus from the other side. From other side, these 2 are there. Don't get confused. 2 are there. 2 are there. But from the other side of the focus, it goes. From other side of the focus, it goes. So here they meet. From the optic center, it goes and it does not get any deviation. So here the image is formed, which is between F and 2F. It is formed. That side of the lens, real and inverted, these 2 are meeting real. I am not drawing any dotted lines, they 2 meet really. Smaller than the image, diminished. Smaller than object or diminished, both are same. And this is the convex lens. This is the convex lens, I said you. So C1, in some textbooks they will be given C1 and 2F, both are same. So here the object is kept. So what happens? The parallel to the principal axis, here the lens is refracted here, yes, parallel, it passes through the optic center and both will be meeting. Between the image is formed between the F dash and C2, which is inverted, smaller than the object. The sixth case, when the object is kept at infinity, this is the principal axis, this is the object kept at infinity, so we can't draw it. So a ray, suppose a ray is coming like this, another ray, they 2 will meet at the focus and the object will be real, inverted and highly, very small. When you see a distance object, you can observe that very small object is formed. So we will end this session with this, and if you like our video, please share to your friends. Don't forget to subscribe and click on bell icon for any notification. Link will be given in the description. Please follow it. Thank you.